Current affective computing systems analyze human emotion by forcing chaotic biological processes into rigid, predefined categories. Machine learning models look at a continuous human experience and output a label: fear, anger, sadness, or joy. To do this, engineers map subjective states onto a two-dimensional grid known as the valence arousal space. The horizontal axis tracks whether a feeling is negative or positive, while the vertical axis tracks the intensity, from calm to highly excited. Data points are plotted neatly into these distinct quadrants. This mapping achieves high recognition accuracy for immediate reactions, but the moment the stimulus ends, the model breaks down. It offers no mathematical way to predict if an emotion will dissipate in 5 minutes or persist for 5 days. To bridge this predictive gap, researchers turn to multimodal biosensing, integrating metrics from the brain and the body to capture a wider physiological footprint. This involves reading electrical spikes in the brain with EEG, which captures rapid cognitive changes in milliseconds, alongside fNIRS, which tracks slower hemodynamic shifts, measuring the blood oxygenation required to fuel that neural activity. These brain signals are then paired with autonomic metrics, like heart rate variability and galvanic skin response, to record the body-level regulation that follows. But fusing these disparate data streams exposes a critical engineering bottleneck. The sensors stubbornly disagree on when the emotion actually happens. Simply strapping more sensors to the subject and plotting them into a static grid will not solve the predictive plateau. The failure stems from a flawed baseline assumption, treating an emotion as a fixed coordinate in time, rather than a dynamic, moving physical process. This chart shows the exact temporal mismatch that occurs when a subject is exposed to a single emotional trigger. The electrical waveform from the EEG reacts almost instantaneously. It registers the initial cognitive processing in a matter of milliseconds. The fNIRS waveform lags significantly behind. It takes several seconds for blood flow to physically travel and meet the increased neural demand. Finally, autonomic bodily responses, like skin conductance, peak even later, creating a delayed, body-wide reaction. When we mark the climax of each wave, the points form a jagged, diagonal staircase. In conventional neuroscience, these temporal discrepancies are dismissed as biological noise. They are treated as artifacts that must be filtered, realigned, and smoothed out until the computer can pinpoint one theoretical moment of peak activation. By forcing these misaligned signals to match, engineers are destroying the specific data required to map how an emotion physically travels through human anatomy. The Brain Kinematics Model offers an alternative framework. It abandons the idea that an emotion is simply a localized brain region lighting up, defining it instead as a distributed kinematic configuration. Under this model, an emotion is a continuous physical strain. It accumulates, propagates, and redistributes across large-scale neural networks. To measure this, we have to stop treating our biosensors as static cameras taking snapshots and start using them as flow meters. In this framework, the EEG tracks fast strain flow dynamics, registering the initial impact as it ripples through the neural network. The fNIRS modality maps the accumulated strain loading, measuring the actual metabolic weight of the emotional demand placed on neural tissue. And the autonomic metrics record the body's mechanical attempt to regulate and safely redistribute this internal tension. This reframing relies on a concept known as the time-variant mismeasurement gradient. The gap between these sensor readings is not an error. That specific interval of time, delta t, is the propagation delay. It is the exact duration required for the strain to physically travel from one network structure and load into the next. These gradients expose the hystereses of the brain, the energy dissipated as neural tissue resists the incoming emotional load, and the slow mechanical process of relaxing once the load is removed. What affective computing previously discarded as biological noise is actually a high-fidelity topographical map of tension navigating the brain's viscoelastic medium. Because an emotion moves, measuring it requires mapping its complete historical trajectory, from the initial onset to the final physical settlement. This trajectory forms the fundamental geometric shape of a kinematic emotional episode, the strain arc. Every episode begins at a resting baseline. As the sensory input strikes, the network enters the loading phase, and the physical tension spikes upward. The network absorbs the demand, moving through accumulation until it reaches maximum capacity at peak strain. When the stimulus ends, the brain begins redistribution and relaxation. This descent is gradual, requiring more time to dissipate the energy than it took to generate it. This reveals the core property of a viscoelastic system. The unloading path does not perfectly retrace the loading path. The biological structure does not immediately snap back to its original state. The network settles at a higher baseline. This gap is the residual strain, the lingering physical footprint left behind by the experience. By plotting hundreds of these arcs across multiple sensors, researchers can deduce the dominant three-dimensional activity pathways, tracing the exact routes the strain took from temporal memory out to prefrontal regulation. An emotion never simply turns off. Its kinematic footprint permanently alters the subject's biological baseline long after the trigger is gone. Translating this theoretical arc into a functional tool requires extracting it from the chaos of raw surface sensors. The engineering pipeline begins by synchronizing all of the disparate brain and body measurements to an absolute shared timeline, ensuring millisecond-level alignment. Once aligned, the modalities are unified into a single metric through a specific mathematical formulation. This creates a strain load index. It integrates the fast neural oscillations, the slow hemodynamics, and the autonomic bodily rhythms into one variable, S of t. While this equation doesn't measure direct mechanical force, it provides a highly accurate calculated proxy for the hidden physiological strain. The equation requires individual calibration. The variable weights must be precisely tuned to account for each subject's unique baseline reactivity. Calibrated correctly, this index acts as the explicit mathematical bridge between a subjective psychiatric assessment and objective modelable physics. The output of this equation exposes exactly why traditional affective computing falls short. Consider two entirely different emotional episodes that register the exact same peak arousal level. Curve A returns rapidly to zero, while curve B exhibits a massive, drawn-out decay over several hours. Standard machine learning models, relying entirely on peak activation, classify these two events as having identical emotional intensity. They ignore the timeline entirely. True emotional intensity is determined by the mathematical integral of the strain load over time, not its momentary peak. The volume of that shaded area represents the total accumulated network loading distributed across space and time. It is this massive accumulated load and the resulting residual strain that drives long-tail cognitive processing. This lingering tension dictates whether the experience results in temporary mood alteration, long-term memory consolidation, intrusive thoughts, or deep dream incorporation. To build machines that can truly track human experience, we have to stop classifying discrete moments of peak activation. We must start measuring the continuous viscoelastic physics of the mind.